Okay, Assalamualaikum warahmatullahi wabarakatuh and good day. We continue our session 3 diesel cycle in part number 2. In 4-stroke compression ignition engine or diesel engine, it almost similar with the petrol engine where they have a intake stroke, and then compression stroke, power stroke, where the fuel was injected into the cylinder, and then lastly exhaust stroke, where exhaust valve open and all combustion product will be now let we see how we can interpret these 4 processes of diesel cycle to the PV diagram. Okay, as we can see here, this is an actual diesel cycle. Where in this point, in this line is actually the intake and exhaust line, and then this is compression, and then combustion, and then this is expansion, and then into the exhaust stroke. As we can see here in actual diesel cycle, we can see that the pressure is similar. The pressure is same for combustion stroke. Okay, so by using air standard assumption, we again we simplify the diagram, the PV diagram of diesel stroke of diesel engine to the PV diagram. So this is ideal diesel cycle diagram, PV diagram. Okay, as we can see here, that from 1 to 2 is isentropic compression process. Okay, similar with Otto cycle. Okay, all same with Otto cycle, isentropic compression process from 1 to 2. But what is different is that from 2 to 3, the combustion process, 2 to 3, in ideal cycle we call it as a heat addition process. In Otto cycle, in this process is constant at volume. The volume is constant, but for diesel cycle the pressure is constant. Okay, and then the cycle moves to the 3 to 4, where it is isentropic expansion, and the last one is same with Otto cycle, that is 4 to 1 is exhaust stroke, or in ideal diesel cycle we call it as heat rejection from the cycle. Okay, from the last slide, they show you the PV diagram of the diesel cycle, but we can also draw a diagram of TS diagram, where in this TS diagram we can see clearly from 1 to 2 is isentropic process, because the entropy x-axis is entropy. So we can see that from state number 1 to state number 2, the entropy is the same, and therefore it is isentropic process. And also goes to the 3 and 4, where it is also the isentropic process, because the entropy is the same. So we can see clearly here in TS diagram. Okay, what is one more thing different? The difference between Otto cycle and diesel cycle. In diesel cycle, we have another ratio that can be used. In Otto cycle, we only have compression ratio RV, where it is a maximum volume over minimum volume. So maximum volume is at 1 and minimum volume is at 2. But in this diesel cycle, we have another ratio. We call it as cut-off ratio. Cut-off ratio, RC, cut-off ratio RC, where it is actually the volume after combustion process over volume before combustion process occur. So it is V3 over V2. And therefore, the processes of ideal diesel engine is consists of four processes. One is isentropic compression from 1 to 2, and then from 2 to 3 is constant pressure, okay, constant pressure, heat addition, and 3 to 4 is isentropic expansion, and last one is process 4 to 1 is constant volume heat rejection or cooling. So thermal efficiency throughout this chapter is remain the same, that is work net over Q in. Work net over Q in. Okay, in this slide, we can see the table, and in this table we will see the related formula that will be used for each processes to analyze our diesel cycle. Okay, same with the Otto cycle, process 1 to 2 and 3 and 4 is isentropic compression, isentropic compression, isentropic expansion. For isentropic, we will use this formula. We will use this formula, exactly the same as Otto cycle. And from process from 4 to 2, that is constant volume heat rejection, also same as the Otto cycle, that is Q equal mc delta T. Okay, the only difference is the process 2 to 3, where the heat addition in Otto cycle process is at constant volume, but in diesel cycle the heat addition is at constant pressure. Okay, is at constant pressure, and therefore the formula is exactly the same, but for specific heat we will use CP, not CV. Okay, not CV. CV is for constant volume, but CP is for constant pressure. So please be extra careful in diesel cycle for diesel cycle, we can use thermal efficiency formula as shown in this slide. This formula only use compression ratio, and cut-off ratio. So this formula was derived from our general equation that thermal efficiency equal work net over Q in, and we substitute the Q in and Q out to the general formula of thermal efficiency and simplify it by substituting compression ratio and the cut. Okay, for process 2 to 3, constant pressure, where the pressure at 2 and 3 is the same, we try to apply this at this both states the ideal gas equation PV equal mRT. We know that pressure is the same, mass is the same, and gas constant is the same at the state number 2 and 3. If we apply this equation, we will have this ratio. Temperature at 3 over temperature at 2 is actually equal to the volume at 3 over volume at 2, where this is actually the cut-off ratio. And then for process 3 to 4 is actually isentropic process. Okay, so we know that volume 4 over volume 3 is actually 4 is actually equal to V1. And by substituting V2 in this equation, we can have compression ratio. Okay, so and therefore actually V4 over V3 can be replaced by compression ratio over cut.